Hi, welcome back. My name is Gilmans, and this is the second episode of my devlog videos. So, on the first episode, we talk about Stellar, a blog post that I did about SES, and lastly, we spoke about Initium. So, this episode will start with Initium. Then a quick blog post that I did, and finally about a new thing that I'm working on. Okay, but first things first, and let's talk about Initium and development progress on the bootloader. Okay, I had a lot of step backs on the bootloader these last weeks, and that is one of the reasons why I didn't devlog video first. But I decided to show you the struggles of of my decisions and why that decisions are bad, and what I will try to do to improve things. Okay. Well, for the ones who don't know, I believe a lot of you don't know. I start developing systems, bootloaders and kernels somewhere around 2010. Okay, it's just a hobby thing. Not, unfortunately, is nothing professional, but is a area that I really like, and I'm have a passion for it. So at the time, I developed a bootloader written in C, and I had a lot with C. I have a lot of freedom on how to do things, which sometimes is good, but the major of the times is a bad thing. Okay, because you will do things wrong or taking bad decisions, mainly when you are new to the things and you don't know the concepts very well. So at the time, I decided to implement built-in commands. So built-in commands will be commands executed by the bootloader shell that give us information about the current machine status. For example, time, resolution, volumes connected to the machine, and consoles, but also commands that allow us to manually load a kernel, or, for example, if you are developing to the UEFI, which is the case here, loading other UEFI applications. So I'm on that. I decided to, weeks ago, starting developing these features on my new bootloader written in Rust, in Initium. Okay, and and I try to use the same approach. So what I did on the past on C was creating a new section on the binary that will contain the built-in commands. So I was able to iterate through that section to find the command that I needed. Okay, let me drink a bit of water. Okay, so I was trying to do the same thing on Rust, but it's not a good decision. Okay, let's start on how I'm building the things. So if I was implementing this on C, I will need assembly to start the machine, even you with UFI, because I will need a way to ensure a easy way to ensure the outputted binary will be recognized by the UFI. Okay, and UFI specifies that the binary must follow a PI format, or portable executable, which is the format that Windows uses for their applications. Okay, and also keep in mind that the calling conventions used by UFI is also from the API that Windows uses, which is Windows 64 API. And that means that the API defines the way that arguments are passed to other functions, and how the return is given to other functions, and that kind of stuff. Okay, for example, on the Windows API, the local variables are stored on stack. Okay, and on other calling conventions, they, for example, can use more registries and less the stack, or some things like that. Okay, for example, on Linux, if I'm not mistaken, arguments usually are passed through stack to the other classes, the other functions. But on this API, usually there is used certain registries to at least pass the first arguments of the function. Okay. So with that in mind, which is important, we need to memorize that those registries, two registries in this case, will be used by the UFI to pass the image handler and the address for the system table, which contains all the functions that we can call or do queries to the UFI, okay, to the firmware. Okay, let's see a bit of code just to help me explain the things. On Rust, we have the ability to define custom targets. Okay, this is possible because Rust uses LLVM as a backend. Okay, and LLVM allows to not only specify configurations for the targets, but also the linker that we want to use. On the UFI case, we use the Rust LLD linker, which is a linker that Rust provides that is based on the LLD linker from LLVM. This linker, if you go to the terminal, usually this tool is internal, but I put the binary path on my global path so I can execute directly. So if we execute like I was saying, if we execute the command, we will get the all available flavors of the LLD. Okay, so LLD can be used to produce Unix binaries, macOS binaries, Windows binaries, and also WebAssembly. Okay. On how our case, we are using the LLD link flavor, which is for Windows, since UEFI understands portable executable binaries. So the flavor is defined here, and the link flags, the linker flags or parameters are linked, are defined here. Okay, so on this, with this command, the subsystem, we are saying the portable executable binary we is EFI application. Okay, this will define a specific bit on the headers of the file to tell the UEFI, the firmware, that this is in fact a UEFI binary. Okay, and this other command entry will define the entry point of the application. In this case, EFI main. Okay, the EFI main, if we code the lib, is defined here. Okay, and we define as an external function to be available to the link to the linker. Okay, as we can see here, the EFI main function receives two parameters, which is image handle and the system table. Okay, the image handle is ignored. We don't need it for what we are doing, but we need the system table, since the system table has all the functions that we need to make use of the firmware abstractions. Okay, so this type of target doesn't allow to use a linker script. Yeah, like this one. This is a linker script that I used to produce a ELF format to the i386 architecture, and with the entry point underscore start, which is assembly code. Okay, nothing fancy. Okay, it's just simple code that I did to do dummy tests. Okay, in fact, this is a previous version because I discarded all the changes that I was doing. Okay, but I don't know if I still have here. Yes, I have another small test that I was doing. Okay, so with this linker script, my goal was to create a specific section on my binary. Here it is, the built-in section. Okay, and with the built-in section, I was also defining these two new symbols. Okay, built-in start and built-in end. These symbols would be storing the addresses that matches with the start of the built-in section and with the end of the built-in section. With this, I will be able to iterate through the section, okay, until I find the comment that I want to execute. Okay. So just to simplify things, the binaries usually have three major segments, okay, which is the data segment, okay, which is only read-only data, or the static constants. I will say variables, which okay, is a static variable, but is in fact a constant. Okay, and on this section is where we put, for example, strings. Okay, or other data structures that are only read only. Okay. For example, if you are writing C and you on the printf, you as a first argument you pass the format of the string. For example, my name is %s. That string will be stored on the data segment because it's a read-only string, and that string will not be changed during the entire execution of the program. Okay, so data segments have read-only permissions. Okay, there is a text section, and this text section contains the code, okay, of the program, and this section has the execution permission enabled. So with this, you can you say to the machine that this part of the code, the binary, is code and must be able to execute. And finally, we have the other major segment, which is BSS, and BSS is like temporary variables, or places where variables will write to. Okay, not all temporary variables or local variables will be stored on this place. Okay, that depends on the type, on the calling conventions and the platform that we are targeting. Okay, in some platforms we use part of the stack to store local variables. Okay, on the other cases we use more CPU registries, or we use parts of the binary that are specially designed per se to be changeable. Okay, so the BSS segment has the read and write permissions. Okay, and usually here we disable the execution permission, because if we have the execution permission on the BSS segment that allow an attacker to use this segment to use some kind of input on your program to put code in and do arbitrary code execution. Okay, so we must ensure that this part and kernels must ensure that this part is not executed. Okay, so I spoke about ELF format. Okay, on this, because ELF allow us to specify the organization of our binary. Okay, but on the case of using the LLD link flavor that automatically produces a PI format, we don't have this ability. So I can't add a new section, or at least I can add a new section, but I don't have the ability to organize in this way, and don't have the mechanisms to create symbols to define the start, to add the start and the end addresses of the section that I want to create. Okay, so we have a problem here. So what I tried to do was to follow an approach that I did in the past when I was reading Initium in the C version. So what I did was producing a health format. Okay, health file is just a format of file usually used on the Linux or the Unix systems, and this file have a structure header that defines sections and of the which is the program header table that defines all the sections of the program. Okay, basically the section specification is used by the kernel, for example, or a platform to jump into the right positions. Okay, for example, these headers have the entry point of the for us to execute the binary. Okay, but health formats are not supported by UEFI. Instead, UEFI, like I said, use PE file format, so portable executable format, which is the default format on Windows. And the sections of this file, let me load this here, is completely different. Okay, take a bit of zoom. Is completely different from health. How we can convert a health file into a PI file? In fact, is more or less easy. Okay, there is a command, okay, which is object copy, and this object copy allows us to copy a binary and produces another binary, and this new binary, this target binary, can have another format. And with this and specifying the sections that I want to copy, I'm able to convert the binary, the health binary, into a PI binary. You can see me doing that here. Okay, I'm with this J command or argument. I'm defining this, specifying the sections that I want to be copied to the target file. Okay, and I'm defining the targeting as being a PAI file format that matches the subsystem EFI app. Okay, so this is used to convert the file. Okay, until here, all good. Right? Yeah. Now comes the tricky part. Since the UEFI needs to the PI binary to have a read log section. This relog section is used for relocation, okay, which is parts of the executable that must be copied to some other place, okay, or having the address modified. So what I did was to create a dummy, sorry, a dummy assembly code to achieve that. So the assembly allowed me to create a relog section, and on that section I'm putting some dummy data. Okay, I don't care a bit much about it. And on this section, on the text section, that means codes, with executions, you can see the X here, execution capabilities, we define our entry point, because on the linker file we define the entry as being _start, okay, and this means this is the entry point for which the UFI will jump into, okay, and as I said before, since this uses the API, the Win64 API, we know that the handler is passed through the RCX registry, which is a 64 registry, and we know that the RDX registry have the pointer to the EFI system table. Okay, so since we already know that the data is in place, okay, and we have the variables defined here, or the arguments defined here on the EFI main, I can simply jump into the EFI main function, okay. That that will make the system be able to or the function to receive these parameters. But unfortunately, I have a weird issue. Let me try if I can show you. That makes the system crash. Okay. Okay, I don't have a script to define. Sorry, he's F0. I don't have a script to define the entry points. Okay, and now we will load our executable, and the system crashes with the invalid opcode. Okay, this is not something produced by the firmware or the machine, is produced by Qemu. Okay, keep that in mind. Okay, so if I try to debug this, it's really hard to understand why this is happening, but seems like something is missing on the final binary. Okay, so I can know for sure that this, okay, is being executed, because I can halt the system on this exact position before we jump into the Rust code. Okay. Ooh. Something is wrong. Let me change something here just to ensure we build this again. Okay, as you can see, the system is altered here. Okay, and notice that this time the text doesn't go off the screen. That means that this code here that reset the screen is being executed. In fact, the only thing that is throwing an error is this example code that I have here. This fact, it's just this toString method. Okay, and this is just one of the examples on where the code fails. Okay, in fact, this on the other on my real bootloader, if I can say that, the fail happens on the different position. In fact, it happens here on the check revision function when I use the info macro. Okay, so something is happening here with this toString method or with the toString trait that prevent us from being able to execute this, and maybe something with the compilation process, but this is really hard to understand what is happening. Okay, as we can see, I'm able to print things in the screen. That means the address passed to the system table is the right one, in fact. Okay, so enough of this thing. Let's back to Initium. I think this will not build. Yeah, exactly, because I'm using the old version with a partial old version, because I need to delete this. I need to delete the import of a single code, and I think it's it. Let me see. Okay, yeah, I'm able to execute now. So new things, I'm able now to navigate the lists, but when I hit the end, I can go to the start. And if I'm on the start, I can go to the end. And we can also see on the bottom of the window, no other, we can see the F2 option. And if I hit F2, we go into the shell. Okay, and the shell doesn't have any comment yet. Okay, but I'm able to write and delete things, move the cursor around, and that kind of stuff. This was everything implemented from scratch. Okay. Okay. So the other thing that I was trying to implement, like I said before, was the built-in command. So I have an example here. So this will be a built-in command, and I was specifying the exact command here and saying that this structure should be stored on built-in section. But in fact, this is a bad pattern, because we should treat everything as data, even our peripherals and any hardware on machine, and we should have the less as possible of global variables or static reference to things. In some cases that is required, okay, or we can create workarounds, but can be a lot harder to maintain, okay, because we will need to have all the system state per se moving around with us for every place that we go, and that isn't really easy to do. Okay, so enough of Initium. I will try, as next steps, I will try to move the command registration into a dedicated module, a Rust module, and have it available since the platform, the entry point, to be able to create our registry comments on the platform code as well on the comment part of the bootloader. Okay, so but enough of Initium. I get frustrated with it and I put a stop and move it to other projects that I had in mind for a lot of time. I have done some scratches on the past, but now I'm trying to implement it with some with some really with a lot of tests to cover the execution, having good documentation, and put every thought that I had on the actual thing. But before moving into it, let me go to my blog, and we can see that I have a new blog post. And this time I had an error. In fact, I had this error when upgrading to Big Sur, but now that I did incremental update, I got the same error and I had to do the same thing. So Apple changes a lot of things and one of them was the entitlement needed to run an hypervisor. So this was the previous or the old identifier or entitlement, and this is the new one. So this article explains how we solve this issue on Qemu. Okay. Next, Oxido. Oxido. What is Oxido? Oxido is a set of or started to be a set of monads to TypeScript. In fact, I'm designing it specially to use with Deno, which is a runtime for TypeScript and JavaScript. It's a secure alternative written in Rust to Node. Okay, and on this library, we can find some secure types. For example, let me jump into the code. I have an option type. Okay, this option type, let's go to the tests, is a type that have specific methods to ensure that we don't run into nulls or undefineds, which is a huge source of problems on programming. Okay, so let me see the docs really quick, where I can find the docs. I think I can go to here and view documentation. Exactly. Okay. So we can find the documentation here. Okay. I expose three methods: none, option, and sum. So option can be from of the sum or none type, and this emulates the option type first or the maybe type from Haskell, for example. Okay, and the option provides a set of methods that allow us to interact with the value wrapped into this monet. Okay, for example, I can do a logic operations, or I can, for example, filter the value, or for example, check if the value is inside the option or not. Okay. Other things, other type that I have is the result type. Okay, result. And the result type is for the cases where we have a value or we have an error. So this way we don't use exceptions. Okay, because exceptions are, in my opinion, a bad way to dealing with program errors. Okay, because with exceptions we completely lost the execution flow of a program, because the program will jump into a random, is not a random place, but will jump into the place where the try catches the exception. Okay, so if I'm new to the code base, I will completely lost the track where things jump to when the exception happens. So if we have ability to deal with errors as a normal program state, is the better, because that way we know the exactly flow that our application will follow. Okay, and having that in mind, I also create an executor that provides three functions. One of them is a panic function that throws an exception. Okay. And this type of exception should not be catched, because if we panic, that means this is a really bad thing. Is a really bad thing that happens with our program, and we should not recover from it. But we also have an unsafe and unsafe async for the cases where we are executing unsafe code, or code that we don't control and don't use the result monad. Okay, so this unsafe will protect us from it by executing a given function in a closed context and returns a result with the execution outcome, which can be a value or an error. Okay. I have a lot of plans for this for this library. And right now I'm implementing a trait type. Okay, and this trait will be used to some kind of emulate trait, the Rust traits or type classes of Haskell, and this allows us to define a given trait like size. Okay, and we can, for example, expose a function to make it simple to call and allow classes to implement that trait, classes or any other type. And we can, by using this function, we are able to call a trait on that object. Okay, but we can do other interesting things like defining the size trait and implement it for already existing type, for example, string. Okay? And if we execute the size invoke on the string, we will get the length because that was implemented by this line here. So this is useful to create reusable abstractions and reusable protocols to our code. This follows a similar approach of the ES6 iterable. Okay, iterable is a protocol which uses a symbol to define that allow us to create a custom iterable. Okay, and I do the same thing. I use a symbol. I use symbols. Okay, JavaScript symbols to uniquely identify traits into the types. Okay, and I'm really excited about these possibilities and what this will give me. Okay, or provide me, and these things will be a building block to create more complex stuff. For example, a file system layer to interact with Deno and others, other common stuff that we need, that we do with when developing server-side. Okay, and all this API is designed in a way to feel closer to REST. Okay, and with that, I can easily move between REST code and TypeScript code and feeling the same, have a more or less the same mindset when developing and try to create the code that is safe as possible and try to prevent the common mistakes from happening. Okay, and if you want to contribute to any of these projects for now, but I maybe will move. Maybe I will move. Let me. Okay, let me just go to here. Okay. Yeah, well, okay. Maybe I will move this code into GitHub because the Deno then will only support providing modules that are stored on public available on GitHub. So this this description here comes from GitHub, and I don't want that. I would like to have a specific description of the project, not of the library, not where is the original source code. Okay, and to contribute, I recommend to open a PR on GitLab. You have the address here. But you can also see the code on GitHub if you go to my profile on github.com/Jill0Mendes. You can go to /al-oxido and you see all the code here. Okay, this is a mirror, so every time you push codes into GitLab, it will appear on GitHub as well. Okay, and as soon as we define a tag, a deploy will happen to, or an update will happen on the further part modules on them. Okay, so these all the documentation code will be updated, and I think it's it. I told it for too long. And I hope you find this interesting and useful. Leave some comment on the video. Give it a like, share with your friends if you find it interesting. Yeah. Let me know if you guys want more of this stuff. At least I'm having some fun doing these videos. Well, see you then. Have a great weekend and see you on the next video. Bye.